Welcome back to Elementary Calculus. In this video, we're going to look at Chapter 4, Section 4, which is about derivatives of exponential functions. And so let's talk about derivatives of exponential functions. And the first kind of definition that we need to be aware of is that if we take the derivative of e to the power of x, the result is e to the power of x. So that's an easy one. All we have to do is remember that that is sort of one of the properties that we're looking at here. And next is if we're taking the derivative of a number, a positive constant that's not equal to 1, and we take the derivative of that number being raised to the power of x, then the result is the natural log of whatever that number is times the original expression a to the x. Now, as that exponent gets a little bit more complicated, if it's not just a to the x, if it's a to some function like g of x, then we have to implement the chain rule. So that's going to require us to have everything that we had before, the natural log of a times a to the power of whatever was there before. But now we're also going to multiply by the derivative of the exponent. Now, if the number a happens to be the irrational number e, then the right-hand side of this derivative is a little bit more simple. And the reason is because if my pen works, there we go. If our a value is, I don't really need to circle those, really just need to circle this. If my a value happens to be e, then the natural log of e is equal to 1, which is why in the next statement we don't see it, but really right there is the natural log of e, which is equal to 1. So that has been sort of eliminated. It's not being included. Normally we wouldn't write a multiple of 1, but it's there. Just be aware. So let's give this a shot. Here we want to find the derivative of this equation. So the derivative of y with respect to x will equal, so we have the multiple of -6, and we can sort of factor that out of the derivative process. So we could then take the derivative with respect to x just of e to the 12x. And if we do that, that multiple of -6 will still be out front. And then let's now take the derivative of e to the 12x. What we just saw above is that this equals e to the 12x, and then we have to multiply by the derivative of the exponent 12x. So I'm really doing this step by step. I'll come down to the next line. Here's my multiple of -6. Here is my multiple of e to the 12x, and then the derivative of 12x is positive 12. Multiplying the exponent of 1 times the 12, decreasing the exponent by 1 gives us x to the 0. That's why the x disappears. And so now we have -6 e to the 12x times 12, and then its multiplication from there, resulting in -72 e to the 12x. This is the most sort of broken down piece by piece way to look at this. This is really using the properties of derivatives that we've seen so far, and I've tried to implement them one at a time. Initially, I'm able to factor a constant multiple out of the derivative process. Secondly, we started the process of taking the derivative of e to the 12x. Being mindful of what really is the chain rule, we get e to the power of whatever that expression is, but then remembering that we have to multiply by the derivative of the exponent. And then In this second to last step, I did actually take the derivative of the exponent, and then after that we just cleaned it up with multiplication. Let's see if we can find the derivative of this slightly more complex problem here. The derivative of y with respect to x equals, and here we have a fraction, which means we're going to use the quotient rule. So this is going to be a little lengthy. The result of this process is going to be a fraction. I don't know how long that bar needs to be, but let's start with it there. And we will take the derivative, which is, I call it low, 2e to the x plus 1 times the derivative of the numerator. I was going to write d over dx of the numerator, but we've already covered the quotient rule, so you should be familiar with this. We're just applying it and stirring in some new processes. So the derivative of that numerator is 4 times e to the x times the derivative of the exponent. So in order to take the derivative of 4e to the x, that's equal to the leading coefficient times e to the power, and then you have to multiply by the derivative of the power. Of course, the derivative of x is 1, which is why I would not typically write an additional multiple of 1 right there, but invisibly it is there. According to the chain rule, it is there. So if you want to include this note, I wouldn't necessarily include this right here in my own personal notes, but if you wanted to maybe block off a little additional section where we just described the process of taking the derivative of 4e to the x, and you could put that in there. So we've got low times the derivative of high minus high, which is the 4e to the x, times the derivative of the denominator, which is, there's that constant multiple of 2, times e to the power of g of x, times the derivative of that exponent, which is just another multiple of 1, so I'm not going to write it, and then the derivative of that constant value plus 1 is a 0, so we don't need to include that either. In the denominator, so we've got low d high minus high d low, all divided by the denominator squared, or low squared, or low low. 2e to the x plus 1 squared. Great, so now let's just clean this up a little bit. I'm going to distribute from the right up here. And there's no distributing to be done in the second term, so that's nice. I've got 8. Now e to the x times e to the x is e to the x squared. In other words, e to the 2x. Remember that x to the m to the n is equal to x to the m times n. So we can multiply those exponents together. Therefore, e to the x times e to the x, which equals e to the x squared, can be written as e to the 2x. So you're welcome to include that in your notes somewhere if you would like. I'm going to go directly to 8e to the 2x over here, and we're distributing in times the plus 1, so that's another 4e to the 1x, minus, we've got some multiplication over here. I see the 2 times the 4 gives us the 8. Oh, it's another 8e to the 2x. And it's all divided by that same denominator. These two terms in the numerator are going to cancel out. So if you like to circle those, that's fine. If you like to cross them out, while I don't recommend that because it makes them less legible, you could cross them out. I like to just circle them. That way I know that they're being canceled out, but I can still read them later. Numerator is 4e to the x. Denominator is the same. And that is not much of a rectangle that I drew around that, but that is indeed my final answer. Sometimes that final answer is going to be even more reducible. You'll be able to simplify it further, but in this case, that factor in the denominator doesn't really align with anything in the numerator, so we're kind of stuck with it. So as far as the final answer, I would say that in a calculus class that's a fairly respectable and tidy answer. I'm trying to think, is there anything that we talked about? The derivative of the numerator. Derivative of the denominator is very similar to the derivative of the numerator, except that there was that +1 in there, but the derivative of a constant value is 0 again, so that's why that disappeared. I think that's about it there. Let's see what else we have. So here's an applied problem. A company's total cost in millions of dollars is given by this function. T is measuring time in years. We want the marginal cost when t equals 4. Remember that marginal cost is, or a marginal cost function is found by taking the derivative of the cost function. A marginal profit function or a marginal revenue function can be found by taking the derivative of either one of those functions. Now the derivative process is easier than it was in the previous chapter where we had to use limits, so we're happy about that, but we're still learning some new tools and things that we have to contend with as we take the derivative. So remember also that derivatives involve rate of change, and so marginal cost or profit or revenue functions involve the rate of change of the cost for the cost function. The first derivative, which is the marginal cost function, gives us a new function which describes the rate of change of cost to produce not just an item, but it's the cost as you change from, well, for example here, we're talking about the cost when t equals, or marginal cost when t equals 4. So that is the change in cost in order to go from t equals 4 to t equals 5. So that will be measured in millions of dollars. And let's go ahead and get ourselves a marginal cost value for t equals 4, and then we'll chat a little bit more about the meaning. So first, I'm going to calculate c prime of t, which is the first derivative. You could call it dc over dt, derivative of cost with respect to time. And that is equal to, now the derivative of 140 over here, that's a constant, so that's going to go to 0. If you want to put in a 0 here, you may. And then minus 70 times, now we need the derivative of e to the t. And that is, e to the negative t, and that is e to the negative t times the derivative of the exponent. This is chain rule again. Derivative of that exponent is simply a -1. Therefore, the -70 times the -1 makes a +70, and we have e to the negative t. So that is your marginal cost function. Let's evaluate our marginal cost function for a t value of 4, and I'm going to have to grab a calculator from somewhere. So that is 70 times e to the negative 4. And if you'll pardon me, I will grab a calculator. Here we go. So let's see, I'm in a grapher, but you could definitely do this in a scientific calculator. And a grapher is nice, I can just type in 70, and then I need my e to the x button, which in my TI-84 is in the left-hand column. I have to hit second and then the natural log button. That puts me into the exponent position above the e. And then remember, if you want to type in -4, you have to use that negative button that's at the very bottom of your keypad. Don't use the minus button. If you're in a scientific calculator, there's also probably a negative button or a button down here at the bottom which has like a plus and a minus on it that'll allow you to toggle between positives and negatives. And that's it, 70 e to the -4, enter. And I got 1.282. So I'll put a squiggly equal sign telling me that this is an approximation, 1.282. That was a very strange looking 8. Let's do better. 282. What that means to me, and now remember that this is a number being measured in millions of dollars. So depending on the scenario, you might need to be giving an even more accurate answer or including more decimal places so that when this is multiplied by 1 million, if you need accuracy down to the penny, then you would want to include 8 decimal places after this. All right. But for the moment, what this means is that the marginal cost of production is going to increase by $1.282 million on your way from the 4-year mark to the 5-year mark. So maybe the company is growing, producing more items. If that cost function also includes overhead, maybe it's anticipated that overhead is going to be growing. Regardless of what's happening behind the scenes, the cost in millions of dollars is going to increase because this is a positive number, positive 1.282. It's going to increase by that many millions of dollars on our way from the input t value of 4 to a time value of 5, in this case as measured in years. How do I know that? Or how could you maybe more easily remember that that's what this marginal cost number means? Because remember that the first derivative is talking about rate of change, and rate of change is change in y over change in x, rise over run, or in this case, it's change in cost over change in time. So if I take this number of 1.282 and I express it as a fraction, and this is being measured in dollars, or millions of dollars actually, and the denominator is being measured in years. If you picture this graphically, this is rise over run, which means the cost in the numerator is rising by $1.282 million, and the run horizontally is a change, not a change in x in this problem, but a change in t. So over the course of that 1 year change in the horizontal direction, we're going to see a vertical change in cost of $1.282 million. That's why, if you've seen in print perhaps, or in another video, that this marginal cost function is described as the change from whatever your input value is to the next input value, in this case from 4 to 5. That's why that's happening, because what we're really talking about here is slope, which is synonymous with first derivative, which is synonymous with rate of change. And I think those are our 2 examples that give us practice with those new features or processes in order to take a first derivative. I hope those are helpful, and I will see you in our next section. Thanks so much.